Hi, my name is Acon. Welcome to the QUICKSURFACE demo. In today's video, we'll be looking at this turbine part and see how we can reverse engineer it in QUICKSURFACE. So QUICKSURFACE is a standalone reverse engineering software that can convert your scan data to a 3D CAD format, and that's exactly what we're going to do in this video. So this part was acquired by a Scanteg's new iReal M3 scanner, and it looks really good to me. As you can see, it's really high resolution and all the details were preserved. So how can we model it up? How do we make this model? From a forward engineering perspective, this is really straightforward. You can just do a kind of a revolve command to make the body, and for the blades you can make one of them and duplicate all the rest of them in a circular manner. But how do we do that in QUICKSURFACE? How do we do that in the reverse engineering workflow, especially if you don't have a perfect part like this one? You can see a dented area here, so this part was probably hit by something before the scanning, and also you got lots of noise and uneven surfaces here and there. How do we overcome all this in the workflow? That's what I'm going to explain in this video. So I will show you all the steps that was recorded in the history tree in QUICKSURFACE. But remember, this is not a tutorial, so I'm not going to explain all the details of each command. Otherwise, that will be a 3-hour video. So I will let you know how we use each command in the whole modeling process, but I'm not going to explain the details. That said, let me just show you the UI of QUICKSURFACE. So we have a bunch of different modules on top of the toolbar, and we have a top window here showing all the different objects by categories. So you have your meshes, you have solids, sketches, and different primitives like planes or cylinders. And we have a history tree on the lower left window. So these are just steps of the modeling process. And now you see some strange kind of ghost shadows on some of the objects at the end of the name. I just installed the latest version of the software, and probably because my GPU or something else, I'm not sure why it appears. I'm actually talking to the developers of the software and see if we can fix that in the next version. But anyway, this is the history tree. This is a parametric system, and I'll explain it later. So the very first thing that you probably want to do after importing your scan data into QUICKSURFACE is decimation or reduction of the polygons. So you can go to scan data, reduce polygons, and assign the target triangles or percentage. In that way, you can reduce the number of the polygons to some extent that you feel comfortable with your PC specs. In my case, I reduced the polygons from 2.6 million to 800K, and that makes my browsing of the objects quite smoothly. So I was using the 800K one through the whole modeling process. The second step of the reverse engineering process is alignment. So you probably want to move your STL file to the origin of your system coordinate. So let me just turn that on. So that's what we want, to put your part aligned with the system coordinate. So how did I do that? So let me just reverse everything back to this step. So what we usually do in QUICKSURFACE before alignment is to extract some primitives from the current mesh data, and then we use the primitives to align or drag the whole STL file together to the system origin. And what I first did is to extract a plane using this area. So as you can see, this area, the circular area, represents a plane very well. So what I did is to hit the extract primitives bottom and just use some of the selection tools on top of the window and select this area before I hit fitting the plane with that. And I've already done that, so I'm just going to hit no. So as you can see, this plane represents that area very well. If you perform compare or what we call the deviation analysis here, you can see they match really well. Okay, so that's the plane, and we can extract like a cylinder using the central hole. So as you can see from the edge of the hole, it represents a cylinder really well. So if we extract a cylinder, we can make use of it. If we compare, you can see that fits really well. Okay, so we have a plane and a cylinder right now. We need to use these two guys to align the part to the system coordinate. What I did is to align by coordinate system. So in this window, you can assign the primary feature and the secondary feature, or even a tertiary feature in the order of priority, depending on which one is more important than the others. On the software, we'll just use them to align to each of the system planes or axes. And that's what we have. So right now, it's already aligned to the system coordinate, and we can start the reverse engineering. Alignment is really important because that gives you a good start. If you don't have a good alignment, all the rest steps are just based on, a problematic beginning. All right, so we'll probably just follow the strategy that I just described that we could use in the forward engineering by making the body and the blades separately. So for the body, we can make a 2D sketch like this. So I'll just turn off the coordinate system so you can see better. So this sketch represents the body, and if we perform a revolve with that sketch, we can have the body. Simple. So how do we do the 2D sketch? So here I would like to introduce a selection status. So that's a selection status for the body making. So you can enter the edit scan window and use the selection tools here to select the region that you're interested for the 2D sketch making. In this case, I believe the red color represents the body really well. So you might have noticed that I didn't select this area because, like I said, it's a dented area. It doesn't represent the original shape of the design. So I don't want it to confuse the system, so I didn't select them. But it doesn't matter because you will see an option in the 2D sketch window to overcome that problem. So after selection, you can save your selection status. In this case, the body one. Okay, so now you can make a 2D sketch. If you hit 2D sketch bottom, you can see the window allows you to choose if you would like to use a sketch for extruding or revolving. In this case, we want revolving. This part was aligned with the Z-axis, so I will choose Z-axis as a revolving center. And here comes the point. You can select the stacked sections. In that case, as you can see from the screen, we have 20 different sections across the Z-axis 360 degrees, and the software will stack or squeeze all these 20 sections into one. In that way, we have more data showing on a single 2D sketch, and we can just draw the 2D curves or lines in the middle of the data. That way we can have our drawing match the geometry more precisely, averagely. Okay, so I've already done that, so just cancel that. So this is our 2D sketch. All right, just deselect all, and I'll hit space bottom to hide the mesh. So this is our 2D sketch for the revolve command. The white points are from the stacked sections that I just described, and the blue lines and curves are the 2D sketches. We have a bunch of different tools in the 2D sketch window that you can use. So you can draw lines, arcs, and some regular freeform curves in the 2D sketch module. And like I said, we have 20 different sections stacked into one. So when you draw the lines or curves, you will probably choose to put them in the middle of the point kind of clouds. In that way, our 3D model will match the shape more precisely in average. Okay, so that's a 2D sketch. You can use a bunch of constraints to make the drawing better, like you can assign horizontal or vertical constraints, and you can assign a radius of each arc. Also make sure your 2D sketch is a closed loop, so you get 3D solid after revolve command. So you connect all the endpoints and add those tangent constraints when needed. So anyway, you just need to spend some time in 2D sketch to make sure your profile is well presented. Alright, I'll just cancel that because I've already done that. And now we have a 2D sketch. We can go to the next step, revolve command. So after revolve command, you have a very good shape for the body. I'll just hide the mesh so you can see better. So that's our body. It's a solid. So if it is a solid, software will just mark that as a solid. If you see a surface body here, that means your 2D sketch is on the closed one. You probably need to go back to the 2D sketch and fix that. Okay, so now we have a body, and now let's make the blades. I'll hide the revolve the body and go back to the mesh. So for the blades, you probably need to pick one of them and model it up before you perform a circular pattern. So what I did is to use the fit surface feature. So in this feature, you can use the same bunch of selection tools to select an area like this. So this is what we call the magic wand. Use the curvature-based selection, and after selection, you can just fit the area with a surface. So we have a bunch of different options here, but the most important one is the analysis one. It's kind of the same as a global deviation command, compare there, which allows you to compare your fit surface with the mesh geometry underneath. So as you can see, under the 0.5 mil, they match really well. Okay, and by default, we have 40% expansion of the surface area. That way you can perform a trimming or a boolean cutting in the later steps. Okay, so I'm going to cancel the whole process because I've already done that. So I have a fit surface 1, which is here. I have a fit surface 2, which represent the other side of the blade. You might wonder, why didn't I use the thicken command to offset the fit surface 1 to the other side? And that is because the thickness of a single blade is not even. As you can see, it's much thicker in the middle region and a little bit thinner on two sides. And that's why we need to fit the surfaces separately. So now we have two surfaces representing each side of a blade, and we need to make a color to perform the trimming that I just said. So how do we make the color? How does the color look like? So if you think about that, the best bet will be making a revolved shape across the same z-axis, representing the boundary of the blade. That will cut the surfaces best. So what I did is to make another 2D sketch across the z-axis. It is here. So let's go into the 2D sketch, and that's our profile for the color. So as you can see, we have 4 sides of the blade, but I only made the curve matching this side of the reference points. The top one, the left one, and the kind of bottom one, I push the curves a bit further. The bottom one is easy to understand because you want to expand the blade a little bit downward so you can perform a trimming or boolean cutting with the revolved body. But how about the top one and the left one? Let's go back to the 3D view. So if you look at one of the blades with this angle, you can see the top side of the blade is not horizontal. It's actually cut by something in this angle. And that's why I didn't put the curve just on the reference point. I kind of pushed that outward a little bit so I can make another surface to cut it out. Same goes to the inner side of the blade. As you can see, it's not cut this way. It has a special angle here, so we probably need to make another surface to do the cutting. I'll go back to the 2D sketch so you can see that again. So that's here and here. Kind of push the curve or line a little bit outward to do the job. Okay, so we have a 2D sketch, and let's go to the next step. Another revolve command. So hide the mesh here. So as you can see here, we have the color. It's a solid. We have 2 surfaces. And if we do a trimming, what do we have? We have this. So this is kind of our base solid for the blade. And now we need to make 2 surfaces here and here to cut it. And what I did is to create 2 freeform surfaces. So freeform module is one of the most powerful features in QUICKSURFACE. You can basically make anything matching your mesh shape, especially those irregular organic shapes. But here we are just using them for a single curved surface for the cutting purpose. So if you go to the freeform editing window, you will see we have a bunch of different tools to do this. So freeform allows you to use different quads to build your surface, and you can turn on the snapping, so that way you can make sure all the points are snapping to your mesh. And you have a deviation analysis mode as well. That is normal shaded mode, that's a deviation mode. And you have a zebra rendering as well. It's not useful in this case, but anyway, we have our cutting surface here. And before the cutting, make sure you expand 4 sides of your freeform surfaces a little bit more. We do that with the extrapolate command. If you are interested how it is used, watch the official tutorials. And yeah, that's it. That's the freeform surfacing. So right now we have 2 freeform surfaces. We have the blade solid, and then we can do a trimming. So that's what we have. Nice. Next up, we can do a filleting. So fillet is really simple and straightforward. You can pick the edges that you want to add the fillets, and we provide a tolerance mode, which is a deviation analysis again, to let you see how well your fillet is fitting the mesh underneath. Okay, so right now we have already finished the modeling of the blade, and what we need to do now is to copy this single blade across the z-axis so we can have all the others. And this is a circular pattern, very simple, very straightforward. In the window you can assign how many instances that you want to have across how many degrees. I'm going to cancel that because I've already done that, and we have 31 instances in this case. So we've already had the body, we've already had the blades. We can combine them together like this. I'll just hide the turbine so you can see better. And what else? The final step. We can add some fillets around the base of the blades. And that's it. That's our model. So this is the modeling process. Very simple, very straightforward. After the modeling, you can compare your model with your mesh like we showed you before. So the deviation analysis is to let you have an idea of how good is your 3D modeling. But remember, matching the mesh geometry is not the most important thing in reverse engineering. So you see, we have a good matching quality with 0.5 mil, but if I reduce the tolerance to like 0.2, you will see a much worse result. And that's quite normal because your part will never be perfect. You will always have some sort of deformation. It might be because during the manufacturing process, you might have sinks, bulges, your part might shrink, your part can be deformed by daily use, or those deformation can be introduced by your 3D scanner due to the low accuracy. So it's never perfect, and you will see some bluish or reddish colors here and there, especially like this dented area. You got a very bad matching quality, but that's what we want, because if you see a green color here, that means that your 3D CAD data is deformed as well. So you need to keep in mind that reverse engineering is all about reconstructing the geometries with correction and meeting the design intent in mind, more than it is about perfectly representing the shape. That is very important. Okay, that is the part and everything that we want to show you in today's QUICKSURFACE demo video. If you have any questions, or if you're interested in QUICKSURFACE or ScanTech scanners, leave your comments below and let us know. Until then, I'll see you next time. Thanks for watching.